Now I'll try to go quickly. Again, you will have the slides. So this is the work that has been done with Total. So taking the same consideration as I just mentioned, we ported the code from Total on GPUs. So their codes, the RTM codes, were not CPU enabled, and the purpose was to have code running efficiently on new architecture. So we used the potential of the system. So high CPU, GPU bandwidths required because the data in RTMs are very large. The unified memory allowed us to do a lot of optimization, and the cache line granularity with the reductions that are required with the boundaries, it helped us a lot to minimize the transfer that we were doing. So something that is important to notice is, again, when we started to work with the team, it's the numbering of the NUMA node. So in Intel, it's 0 and 1. On Power, it's 0 and 8 for the main memory. And then you have the NUMA node 252 to 256, 255, sorry, that represent the GPUs. The first rule is usually don't bind any memory on the GPU unless you know exactly what you are doing. Usually what you want to do is to start your process on a given NUMA node from the CPU, and then your application will use the other memory. Later, there can be optimization that can be done with this NUMA node, but the first rule is really to focus on putting the memory on the CPU only first. So the main technical challenge, so very quickly we figured out it was not really a problem of algorithm, but it's really a problem of memory, both memory on the CPU and on the GPU. So in the case of RTM codes from Total, we did not go with Volta 32 GB GPUs because thanks to the bandwidth provided by NVLink, it was we were able to really optimize the transfer between the use of central memory versus the GPU memory and data transfer. So typically each chunk of data were at maximum 7 GB. So we were able to move one chunk at a time, do the computation, and move the other. So it was very convenient. So once we think about where the data would be, how to manage them, the second part was to extract parallelism. Specifically for RTM, it's really easy. So it was not a big challenge to do the compute optimization. And then the second part was to optimize the communication. At first, it's always better to keep everything synchronous, simply because there can be a lot of things going wrong, because the way we understand CPU working, CPU code, and the way the GPU will work is completely different. Typically, I didn't mention that, but on the SAXP example, we had a specific test to check if the index is not exceeding the size of the array. So it's a typical error that we do when we run on GPU. So that's why it's always better to start with synchronous application. And after being sure that the synchronous part is working, you move to asynchronous parts, especially to overlap communication and computation. So again, it's really easy to do that with GPU because the streams that are doing the computation and the computation are completely independent. So that's something that yeah, can be done quite easily. One key point, and I will show an example after, it's to optimize the GPU kernels. And it's something that is unfortunately right now very specific to NVIDIA. I don't know how ATI is doing that, but on NVIDIA, all the kernels are run in streams, and you can create multiple streams, schedule them like you prefer. It allows you to overlap all the computations that you are doing on the GPU. And again, I will show an example after. And then you are using additional optimization for communication. So overlap, of course, the use of GPU Direct. Sometimes you don't need to move back all the data to the main memory to do an MPI communication. Maybe you can simply communicate between GPUs. So this is a good optimization also. And then you do some GPU kernel optimization. There is always optimization to be done. And at the end, we came back to the CPU code and see if there were no additional optimization that could be done on the CPU. Typically, we found out that it would be a good idea to use the compression instruction on the power 9 to optimize the last compression of the to use less memory. Then from the application optimization strategy, it's very important to understand what is the objective. Is it pure performance? Is it a production and total cost of ownership focus? Is it energy? There are a lot of parameters to take into account before choosing the way we will optimize an application, and especially the programming model that we'll use. So usually people are targeting something that is portable. So something that is not specific to a given CPU or GPU. And that's why the programming model, directive-based programming model like OpenACC and OpenMP are good to use. After that, it's always complicated to be completely hardware independent because optimization are always linked to the capacity of your system. So there is always some small bits that you will still optimize to gain 10% on a given architecture, but that won't be usable on the other. So the focus was, again, first to extract the parallelism, and especially the data parallelism, which is actually the most important. Then understand how we would manage the memory. Then concurrency of all the thread and the asynchronism that we can use, the communication schemes, either GPU direct, yeah, I will give the example after, it will be easier, either GPU direct or moving back to CPU and so on. So there is a lot of things to be done here. And then there is always runtime optimization. Typically, with the first version of the application, we have been using two processes per GPUs because one process was not able to fully utilize one GPU. But with later optimization, we saw that it was better to run with a single process per GPU. So depending on the state of optimization of the code and so on, the runtime optimization will be can be very different from one to another. Yeah, so memory management, it's important to figure out CPU, GPU, where you do the allocation. Blindly, when I was first doing GPU code, I was first allocating everything on the CPU and then moving the data when I needed them. But sometimes you don't need to do that. So what you do is to really understand where you will need this memory space and where it's best fitted to allocate and transfer the data. So the memory allocator is also very important. We have seen different kind of performance. No, most of them are fixed, but yeah, it can be also a big issue. Yeah. And then there were some GPU-specific tuning. So new function on GPU were moved first with OpenACC. And we also put additional CUDA optimization. So that's something that is working well on NVIDIA device. So you put OpenACC directive, but also CUDA functions to optimize, to fully optimize your code. And then, of course, the asynchronism that we talked about a lot. So here it's an example of I would say assembly code optimization with CUDA. So all the compute kernels are using OpenACC, but here we are declaring additional stream for the GPU. So it's unfortunately right now you can only do that with CUDA. So once you have created your CUDA stream, what you do is you associate, yeah, one good thing as well, and I will come back to that, is to also to name your stream so you understand what it's doing. And once you have created all your CUDA stream, you can associate a CUDA stream with ACC. So it's one of the key optimizations that we have been using for fine-tuning the application at the end. Another key point when you do when you port application to GPU, it can be a good idea to leverage the NVIDIA NVTX API because typically here, sorry, what you would do, you push a tag on your function, and then when you run with the profiler, you directly have the name of the function instead of kernel, blah, 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 blah. You directly have a name that you can comprehend and understand what it's doing. So you can always go back and have the link to the code and see what it's doing, but having the time view, timeline, sorry, with the name of something that you understand is always a good thing do. I agree, it's something that is a little bit assembly code, similar to assembly code, but at the end, for the system, it's good to have it. And an example of leveraging both GPU and CPU. So I'm not an expert, but what is important in the RTM, I've been told, is the wavelets. So it's the image of the wave that you have sent on the Earth or the water, and this problem is the image is quite large, and if you want to save both memory, central memory, and disks space, it requires to have some compression. So the compression is happening in two ways. There are some very high level quantization of the wavelets that are made. It's already, I think it's about 10% that remains after this quantization, and then the data is moved to the CPU. During this quantization, there is a little loss of accuracy, but given the amount of memory, that's something that's reasonable. And then we do a second optimization on the CPU, where we compress with the hardware gzip function to get optimal data size at the end and memory utilization. So that's something that unfortunately you can't do right now with P9 using the gzip, but that's there are other functionalities of the P9 that can be leveraged. So it's an example of final optimization that you can do for your code. So I miss the important point at the beginning. It's important to also rework when we port application to GPU. It's also important to rework CPU parts because the behavior of the CPU part will also change. So it might require some additional optimization